Hello, everyone. Today's question is peak index in a mountain array. So the question is, given an array guaranteed to be a mountain, find the peak index. So first, let's discuss the properties of a mountain array. The length of the mountain array is at least 3, and there's a value in the array that is greater than the values to the left and right of it. And so at the peak, as we move further away from either side of the peak, the values gradually get smaller. So if we look at this example here, 24, 69, etc., we can see that the peak of this array is 100. And as we go to the left of this peak, the values get smaller. So it goes to 69, and then it goes to 24. And as we go to the right of this value, it gets smaller again, 99, then 79, then 78, all the way down to 19. So the first approach we can take is the brute force approach. Now, we know that we can't start our array at 24 or 19 because they are at the end of the array, and at the first index, there's no left value, and the last index, there's no right value. So we don't want to check those so that we don't go out of bounds. So we'll be doing a linear search from the second index to the second to last index. And at each value, we're going to be checking if it's greater than the right and its left value. And so here's the pseudocode here for I equals 1, I less than the array's length, I plus plus, if there is a value in the array that is greater than the value to its immediate left, and the value is greater than the value to its immediate right, then we're going to return I. Otherwise, we keep looping through this array until we find that index. And as I said before, our array is guaranteed to be a mountain array. So, this is going to have a time complexity of big O of n because we're going to do a linear search. And the space complexity is going to be constant time because we don't use any extra data structures when we're doing this. So that's big O of 1. So now, is this the most optimal solution? So, the short answer is no, but let's go over why that's the case. So, if we know that at the peak index, the value to the as we move away from the peak, the values are going to progressively get smaller, meaning that there's a way for us to cut down our decision space in half every time that we look at a certain index. So we can actually implement a binary search to find our peak value in this array. And so as we go down here, we're going to have the same array again, but this time we're going to walk through a binary search. So we start with our left and right pointers at the two ends of the array, and our middle is going to equal to the left plus right divided by 2, right? And so first we're going to check if the value to the right of it is smaller. The reason being, we'll know that there's no value to the right of it that's larger than this middle index. So first we check that. Then we check if the value to the left of it is greater. If the value to the left of it is also less than the middle index. And as you see here, it's not. So what we're going to do, oh my gosh, sorry about that. So what we're going to do is we're going to set our right index equal to 79 now, because 99 was greater than 79, and we didn't do mid minus 1 like we do in a normal binary search, because we want this potential value to be included in our range for our possible peak. So then we reevaluate our middle, and this time it's going to equal to 100, which is greater than 99, and it's greater than 69. So it checks out. So here's a little boilerplate as to what we want to do as we go through this array. So we want to check if array at mid is greater than array at mid plus 1 first, to know that the right side is smaller. Then check if array at mid is greater than array at mid minus 1. So then we know that there's no value to the left that's larger, because remember, as we go further away from the peak on either side, the numbers are going to be smaller. And so if it passes that, then that's going to be our peak. And if it wasn't larger than this here, then we want to set the left, then we would want to set the left equal to mid plus 1. So here is our pseudocode right here. While left is less than or equal to right, we get our middle, and then we check if it's greater than our immediate right element. And then if it is, we check if it's also greater than its immediate left element. And if it is, that means we found our peak and we return the middle. Otherwise, we set the right equal to the mid, so that we have our new space for our possible peak element. And if it wasn't the case that it was greater than its right element, that means we can go further right to possibly find our peak element. So we would set the left equal to mid plus 1, similar to a regular binary search. Alright, so now we're going to cover the coding part of this problem. So it's pretty straightforward. We're just going to do the same thing that we did on the whiteboard. So we're going to set the left equal to 0, and then we're going to set the right equal to the length of the array minus 1, and then while the left is less than or equal to the right, we're going to be continuously checking if the middle element is greater than both the values to the left and to the right of the array, in the array. That's going to be our peak index. So we set mid equal to left plus right divided by 2. And then if the array at mid is greater than array at mid plus 1, and the array at mid is greater than the array at mid minus 1. What this is our check here. So if array mid is greater than the one immediately to its right and is greater than the one immediately to its left, then we return mid. Else if the array at mid is less than the array at mid minus 1, then we want to set the array, we want to set right equal to mid. Otherwise, we want to set left equal to mid plus 1. So I'll just quickly address why we didn't set right equal to mid minus 1 is because we want to include from the range from mid to the left pointer, because that could be a potential area where we compare left and right values for one of the potential peaks. Okay, and so hypothetically, if we weren't able to find it in the right array, in the while loop, then we would return -1. And I'm also going to add one more check. So if the array.length is less than 3, then we return -1, because that means that we don't have a valid mountain array. And so let's check this out here. Alright, so that's it, guys. Thank you so much for your time. If you would like to join our community, the Discord link will be in the description below. And until next time, I hope I get to see you guys very soon. Thank you.